Lecture 1.17, 17th lecture this year. We're going crazy. Any case, this lecture is about manometers, sometimes called manometers. Either way, these are meters that measure actual pressure. Okay, before we get started with this, let's go file new on just new. Let's talk about what a barometer is first. Okay, now we're going to take a guy named Torricelli, and let's get out of this ink. All right, he took he took a test tube that was very long, skinny test tube. We call them udiometer tubes, and probably about a meter long. Okay, so this whole thing is about a meter long. And what he did was he inverted it. Okay, so he took his test tube. Okay, inverted it. I should have wrote it this way. He filled it with mercury. Now he used mercury for a reason. We're going to get to those reasons. I know it's not green, but it's the best I can do. So he filled it with mercury. Okay, and what he did was he inverted it, put his thumb over the top, and put it in a pan. Now let me show you what I meant by that. So what he did was he made a pan of mercury, and he inverted it, filled this up with mercury. Okay, and he noticed that when he flipped this downward with his thumb on it, big old thumb from a finger, yeah, nice hand. Okay, and he flipped it over, he noticed that when he submerged it in the mercury, some of it fell down. Okay, and that level that he got of mercury suspended in a column, okay, he measured that to be 760 millimeters. We don't need this anymore. So again, at sea level, taking his pan of mercury, okay, with his big, huge test tube, filling it with mercury, putting his thumb over and inserting it underneath the liquid level, okay, and then standing it up, he noticed that atmospheric pressure could support 700 millimeters of mercury high. And this was the first measurement, a quantified measurement with numbers for pressure. Okay? Now, so he said that a height in a column of mercury is a pressure unit. So we still use millimeters of mercury today. Okay, so he said, wow, we can support this much. Now, the reason why mercury was such a great element to use, it was a liquid metal, very, very dense. Okay, in fact, its density is equal to 13.6 grams per milliliter. Remember, this is mercury. Water's density, okay, is 1.0 grams per milliliter. So density, mercury is 13.6 times more dense. Truthfully, it's 13.6 times more massive for the same volume, right? Get out of this idea of density is density. It's a ratio of mass to volume. So for the same volume, mercury is 13.6 more massive. Now, why is that important? Well, think with me, okay? If we take some atmospheric pressure, now, atmosphere is bouncing in all directions, but it also is hitting the top of the fluid. So we're getting bombarded by particles that are hitting the fluid, the top of the mercury. Now this pressure on top of the mercury is pushing the liquid up into the tube. All right, so that's what's keeping it. If there was no atmospheric pressure, this mercury would all fall out. If I was to do this with water, because I can't do this demonstration, I used to be able to do this demonstration years and years ago. Can't have open mercury for good reasons, and there's also some reasons I'll talk about that, raise an eyebrow about it. Any case, the point being is if I take the same barometer, an open flask of water with a tube of the same height, this is all not drawn to perspective, you would see no water falling. Assuming this was 1 meter tall and this was 1 meter, you would see no water. Why? Because water is so light. It's 13.6 times lighter. So the atmospheric pressure pushing down on the liquid, okay, forces all the water up. In fact, as I taught you today, about 34 feet of water is equal to another atmosphere of pressure. So we would need a barometer 34 feet higher, okay, or need a barometer 34 feet high to start seeing a change. The reason why we see a change in the liquid dropping at only 0.76 meters, okay, 2 plus something um, feet, is because mercury is 13.6 times more dense. Okay, now, what are we doing here? Well, we're first describing the pressure due to mercury, height of mercury supported in a column. Okay, we can't use water because we need so much more of it because it is so less massive. The pressure pushing down, the atmospheric pressure, is enough to support exactly 34 feet. So if I had a 34 feet tube, you couldn't measure any changes. But because mercury is so dense, you don't need as much height. Okay, and this is going to help us with some other problems. Okay, so that's the basics. Now, what really is a barometer? Let's get some stuff out of the way here. A barometer is really a manometer, okay, or manometer, as I like to say. I'm not trying to be sexist, but it sounds funny, so I just went that way with it. Okay, so no one really calls it a manometer, but hey, I'm tall. All right, any case, so what are we talking about here? We're talking about suspending the height of a fluid with competing pressures. Competing pressures? What am I talking about? What is the competing forces or pressures here? There's two. There's the competing atmospheric pressure pushing down on a liquid. Then there's also the competing weight of the liquid in the container, okay, or in the eudiometer tube, okay? So we have a force pushing upward on the tube that's atmospheric. Let's pretend it's 1 atmosphere. That's standard pressure, or 101.3 kilopascals, or what? 14.7 pounds per square inch. Any case, so what we have, if I take the tube out of the drawing, what do I have is I have a force pushing upward on the tube. You can think of this force continuing upward. And then I have the weight, which is the mass times acceleration. It's a force downward. So who's winning? Who's winning this battle right here? Well, it looks to me that, okay, we've reached equilibrium. The weight of this mercury pushing down is equal to the force pushing. Now, why do I know it's equal? Because the line is not changing. Okay, if the line is not changing, we're saying that this is equal. Now, how can I draw this? Well, I can draw this in something called, again, a manometer. Watch. Okay, let's take a drawing, and let's take, it's going to look like the best drawing I can. You can tell that my art skills are definitely not there, but here's a container of a gas, and here's a little bit of a U-tube. Looks like a nephron, I guess, of a kidney. Okay, and this is where the gas is. And of gas molecules are flying around, they're exerting a pressure, and I have a fluid in here. Let's make that fluid mercury. Okay, Hg. Notice these lines are level. We have an open tube manometer. Okay, what's pushing down? Let's make it atmospheric pressure, which is, let's make it 1 atmosphere. If I'm pushing down 1 atmosphere on this top of the liquid, and the gas is exerting a pressure down on this liquid, who's winning? Nobody is. Because the levels are equal, we say the pressure in the gas must be equal to the atmosphere. That is how a manometer works. We compare how much it's winning or losing or equal to another force or another pressure over an area. So we would say if it's 1 atmosphere, okay, we would say that they have the same pressure. Now, we also noticed that I can use 700 millimeters of mercury as 1 atmosphere. Right? Yes, of course. And because it was Torricelli who did it, we also call it 760 torr. So you hear torr as another unit of energy, pressure, I'm sorry, is because it was based on Torricelli's measurement of how high in millimeters of mercury. So torr and millimeters of mercury are used interchangeably. All right, what about if the gas is winning or losing? Okay, so let's get rid of some stuff here. get rid of this. All right, let's draw another manometer. All right, in fact, instead of drawing manometers, how about I just change the scenario here? Okay, I don't know if I can do it so well. No, I probably can't. So let's draw quickly another manometer. All right, and again, looks like a nephron. Okay, so this is a pour drawing. Here's a gas in here, and then I have a liquid, and very simply, let's make the liquid do this. And let's fill that liquid up with mercury, Hg. Okay, my friends in chemistry, we have to know some other piece of information. Let's fill this with a color. Oh, I don't want to do that. Fill that with a color. That's not a color. Okay, so there's my green. Okay, so clearly here, party people, the gas is winning. It's pushing back, okay? It's pushing back on this fluid and pushing the fluid up the tube. Now this is an open tube manometer, so atmospheric pressure is pushing down. So if I know the atmospheric pressure, let's say it's 760 millimeters of mercury, or torr, okay? And how much is this gas winning by? Well, if I draw a straight line from where this level starts, I can measure the height in mercury, which is a pressure. The supported, that's a terrible column drawn, so this would be more of a straighter line, but you get the idea. This is a column of mercury, which is what we got from the original barometer. So let's pretend we measured this, and it was 300 millimeters of mercury, mmHg. That's not mm, I can do this. Okay, so we measured this height of column above this equilibrium line, so to speak, and we're supporting 300 millimeters of mercury above this line. The gas is not only pushing back 760 of pressure, it's also doing what? It's pushing back 300. So what's the pressure in the gas in the manometer? It would be 760 plus 300. Why? It's not only pushing back 760, it's pushing back another unit of pressure. We determined the height of column of mercury is a pressure unit. So of course it'd be 1060 millimeters of mercury, or torr. Here it was equal, here it's winning. What do you think the third scenario would be? Okay, the third scenario, and I'll just put it down here, and I'll be finished. Okay. The third scenario is, here's another manometer. Okay, let's say the gas is losing. Okay, again, we're going to use mercury. And how much is it losing by? Well, let's extend this line. Let's make it 300 millimeters of mercury. We have the gas in the manometer, and we have atmospheric pressure pushing down on the liquid. Okay, if atmospheric pressure is 760 millimeters of mercury, or 760 torr, they're interchangeable, or I could say ATM. Okay, but that'd be 1 ATM that equals 760. Okay, clearly the gas, who's winning? Okay, the atmospheric winning by how much? 300. Okay, atmospheric pressure is not only pushing back the gas. Okay, it's basically holding up or supporting 300 torr, or millimeters of mercury, which is a pressure unit. That doesn't mean that the pressure now is 1060. You can't increase this pressure. So the difference in pressure is 300 millimeters of mercury. That means the gas has less pressure than the atmospheric pressure by 300. So in this case, it'd be 760 torr, which is the same thing as millimeter, minus 300 millimeters of mercury. Okay, and of course that would be what? Doing my math in my head, 460? Yeah, I should have been able to do that. Okay, 460 millimeters of mercury, or torr. It's the same thing. All right, these are interchangeable units. So you notice it's less by 300. That's why it's losing. Now these are open tube manometers. There's one other scenario, and that would be a closed tube manometer. A closed tube manometer is like a barometer. Put a gas in here. Look at your liquid. Liquid is mercury. Because this is going to be a vacuum, like we talked about in class today, or any case, there's going to be really no pressure above here, so we're just going to measure this line, okay, that's being supported. Because there's no pressure pushing down, we're just measuring the height of liquid. So if this is a gas, and this is 300 millimeters of mercury, then my friends in chemistry, the actual gas pressure is actually equal to 300 millimeters of mercury. And a closed-end barometer, my friends, is a closed-end manometer is a barometer. You're measuring the height of column. Hey, how does this look compared to what we just did? Barometer, closed end. This is a vacuum. Okay, there's very little evaporation of the mercury. We'll talk about it. There's very low air pressure. All right. So when you do your problems, and I'm going to assign those problems right now through the video. Let's get rid of this. Okay. And let's go to the manometer. Here's what I want you to do. I want you to do these three manometers. Okay, careful of your units. You can assume that these are all going to be mercury. Okay, in mercury in as the liquid for all of them. Okay, and then I would like you to also try number 2. It's a little bit of a stretch right now, but you're going to compare the densities. We'll see how you do on that. Okay, and then on the back side, I want you to do the following. I want you to try all these manometers. Okay, and again, you can also assume that these are all mercury. Okay, notice the different pressures. Okay, careful. So try these, careful of your units. If you have inches, okay, and some of these are going to be more difficult than others. I get that. It's going to be a little bit of a stretch, and I'll review this tomorrow. But let me just talk about it for a second. Remember, it's millimeters of mercury. That's the pressure unit. And of course, you have different units here. So 760 torr is equivalent to 760 millimeters of mercury suspended in a column. That's where we got the original pressure measurement at atmospheric pressure is equal to 1 atm, which equals to 14.7 pounds per square inch, lbs per square inch. Okay, and that's where we get, now the inches, you should remember that 1 inch is equal to 2.54 centimeters. You may say, why are we doing inches? Because some barometers use inches of mercury. Okay, so try. So what you're trying to do is find out what the pressure of these gases are. Okay, considering who's winning and losing and the heights of the column. I do have the key up there, so you try them. All right, and that's what I want you to do. So do number 5. Number 2, and these right here, I'm going to put the key up. Do your best, okay? I'll do one right here for you. Let's do number 1 together. Height is 52 centimeters. 52 centimeters is equal to what? 52 centimeters is equal to 520 millimeters of mercury. All right? So this height is 520. Who's winning? Who's losing? Because it's an open end and the pressure pushing down is 760 torr, which is the same thing as a millimeters of mercury, the gas is losing by 520. So this is going to be 760 minus 520. All right, I'm going to leave it at that and see how you do. If you struggle, it's okay. Okay, we're going to fix this tomorrow, but you should get a good basics or some basics from this. And go back and listen if you have to. This is fundamental, okay, to understanding the rest of this course using manometers. Okay, so I get 240 torr is the pressure, assuming my math is right. Okay, so I'll leave you at that. Take care. Good luck.